are called 7 dimensions of the physical world. They are denoted with square brackets. As we can see here, that relation between some physical quantities in CGS and SI system. Physical quantity force, CGS unit is dyne and SI unit is Newton. 1 Newton equal to 10 to the power 5 dyne. Physical quantity is energy, CGS unit is ERG and SI unit is joule. 1 joule equal to 10 to the power 7 ERG. Magnetic flux, CGS unit is Maxwell and SI unit is Weber. 1 Weber equal to 10 to the power 8 Maxwell. Magnetic induction, CGS unit is Gauss and SI unit is Weber divided by meter square or Tesla. 1 Tesla equal to 10 to the power 4 Gauge. Magnetic intensity, CGS unit is Oersted, or in short form capital O and small e. SI unit is Ampere divided by M, and relation is FT hyphen Poundel. Then we have power. CGS unit is ERG divided by S, and SI unit is watt or W. Then we have relation 1 ampere divided by meter equal to 4 pi into 10 to the power minus 3 Oersted. Then we have a star mark. 1 ampere divided by meter equal to 4 pi into 10 to the power minus 3 Oersted equal to 4 pi into 10 to the power 3 Gauss equal to 4 pi into 10 to the power minus 7 Tesla equal to mu naught Tesla. The Oersted symbol OE in the unit of the auxiliary magnetic field, H in the CGS unit of units. It is equivalent to 1 dyne per Maxwell. Thus length is represented L, mass by M, time by T, electric current by A, thermodynamical temperature by K, luminous intensity by CD, and amount of substance by MOL. Note that using the square brackets around the quantity means that we are dealing with the dimensions of the quantity. The dimensions of physical quantity are the powers of exponents in which the unit of base quantities are raised to represent derived unit of that quantity. Linear momentum, physical quantity, dimension formula m to the power 1, L to the power 1, T to the power minus 1. Force, physical quantity, dimension formula m to the power 1, L to the power 1, T to the power minus 2. Impulse, physical quantity, dimension formula m to the power 1, L to the power 1, T to the power minus 1. Pressure, physical quantity pressure, and or stress, dimension formula m to the power 1, L to the power minus 1, and T to the power minus 2. Physical quantity, universal gravitational constant, dimension formula m to the power minus 1, L to the power 3, and T to the power minus 2. Physical quantity, work, energy, moment or force, dimension formula m to the power 1, L to the power 2, and T to the power 2. Power, physical quantity, here we have a dimension formula m to the power 1, L to the power 2, and T to the power minus 3. Surface tension, we have power here m to the power 1, L to the power 0, and T to the power minus 2. Moment of inertia, m to the power 1, L to the power 2, and T to the power 0. Planck's constant, we have a dimension formula here, m to the power 1, L to the power 2, and T to the power minus 1. Latent heat, we have here dimension formula m to the power 0, L to the power 2, T to the power minus 2. Gas constant, m to the power 1, L to the power 2, T to the power minus 2, K to the power minus 1, dimensional formula. Boltzmann constant, we have a dimensional formula here, m to the power 1, L to the power 2, T to the power minus 2, K to the power minus 1. Stephen constant, we have a dimensional formula here, m to the power 1, L to the power 0, T to the power minus 3, K to the power minus 4. We have magnetic flux, dimensional formula, m to the power 1, L to the power 2, T to the power minus 2, A to the power minus 1. Dielectric constant, we have dimensional here, m to the power 0, L to the power 0, T to the power 0. Resistance dimensional here, m to the power 1, L to the power 2, T to the power minus 3, A to the power minus 2. Conductance, we have dimensional formula here, m to the power minus 1, L to the power minus 2, T to the power 3, A to the power 2. Conductivity, we have dimensional formula here, m to the power minus 1, L to the power minus 3, T to the power 3, A to the power 2. Electric flux, we have dimensional formula here, m to the power 1, L to the power 3, T to the power minus 3, A to the power minus 1. And power of lens, we have dimensional formula, m to the power 0, L to the power minus 1, T to the power 0. So these all are dimensional formula of physical quantity which we have studied right now. Motion, the branch of physics which deals with the study of motion of material objects, is called mechanics. So basically, when we go in physics, where we deal with the study of motion and materials objects, is called a mechanics. Mechanics can be broadly classified into following branches. Like statics, it is a branch of mechanics which deals with the study of material objects at rest. Something which is at rest we call as a static. And kinematics is that branch of mechanics which deals with the study of motion of material object without taking into account of factors, that is nature of force, nature of bodies, etc. Hence time factors plays an essential role. So kinematics is something which is in motion, we call it as a kinematics. It is simple. Note, the term kinematics is derived from the Greek word kinemia, meaning motion. Dynamics, it is that branch of mechanics which deals with the study of motion of objects taking into account of the factors which cause motion. Here the time factors plays an essential role since the force is the cause of motion. Therefore dynamics is based on the concept of force. So basically, when we go in dynamics, so in dynamics we basically see that what are the factors which is causing a motion to any object, and what is the factors which play essential role in it. And since the force is caused by motion, because force is caused by motion only, therefore dynamics is based on the concept of force. So force in dynamics is independent on force only. The term dynamics is derived from the Greek word dynamics, meaning power. Basically derive power. Motion and rest, the concept of motion and rest depends on observer, frame of reference, and object. So when we try to know the concept of motion, so it basically how we take as a frame of reference from where it will go and how it will come to rest after some time. If the position of an object in space changes with time relative to an observer, it is said to be motion, otherwise at rest. Okay, motion can take place in one dimension, linear motion, two dimension, planar motion, or in three dimensions. So basically we can say that they can take place in three kind of direction: linear motion, planar motion, and other kind of dimensions. Type of motion of body, if we go through broadly, the motion can be divided into following three types. Rectilinear and translatory motion are there. If a particle or body treated as a point is moving along a straight line, like if a particle or a body treated as a point moving along a straight line, the motion is called rectilinear. Okay, something which for example, from a point, if somebody is going a straight line, so we call it as a rectilinear motion. Then we have, however, if the body cannot be treated as a point but moves in such a way that all its particles move simultaneously along straight lines. So basically try to keep it easy. So whatever we see that in it is moving in a straight line which are collinear or parallel to each other, so we refer it as a rectilinear. By shifting through equal distance in a given time, the motion of the body is called translatory. So whenever we have equal distance in a given time, the motion of the body is called a translatory. A body slipping along the inclined plane has translatory motion. So body slipping in the inclined plane, like okay, so then it is called a translatory motion. Rectilinear and translatory motion can be uniform or non-uniform. So it can be uniform also and non-uniform. Circular and rotatory motion, if a particle or body treated as a point, it is moving on a circle, the motion is called a circular. Simple. If it is moving on circle, we call it a circular. However, if the body cannot be treated as a point and all its particles move simultaneously along circles, like if someone is moving around a circle whose center lie on a line called axis of rotation, and whose center lies on the axis of rotation from where it is moving, by shifting through equal angle, by his shifting to angle in given time, at the given time, the motion is called a rotatory motion. We call it as a rotatory motion. It is 2D or 3D motion and can be uniform or non-uniform. If uniform, it is periodic, and if it is uniform, we call it as a periodic, oscillatory, and vibratory motion. If a periodic motion is constrained, that is within certain limits or is to and fro, up or down, is said to be oscillatory. Like if it is moving up and down, to and fro, it called as oscillatory motion. If in case of oscillatory motion, amplitude is microscopic. Here amplitude is microscopic. It is usually said to be vibratory motion. Basically, it used to vibrate. In the oscillatory or vibratory motion, if the restoring force or torque is linear, the motion of the body is said to be simple harmonic motion. When oscillatory or vibratory motion, whichever is going on, and there we find that restoring force, whatever torque we called, okay, is linear, the motion of the body, like whatever force has been put up from the other body, and it is handled by the as a other body, said to be simple harmonic motion. So we call it a simple harmonic. An object can be considered as a point object if during motion in a given time it covers distance much greater than its own size. It is important to note that the point object is a mathematical concept to simplify the problems. Okay, motion is one in 1, 2, or in 3 dimension. One dimensional motion. The motion of an object is said to be one dimensional motion if only one out of 3 coordinates, specifically the position of the object, change with the respect to time, or when a body moves along a straight line path. Its motion is said to be the one-dimensional motion. One-dimensional motion is sometimes known as rectilinear or linear motion. For example, the motion of a train on a straight track, a stone falling down vertically, a car moving on a long and straight road, etc. In such a motion, there is no movement of the body in the lateral direction. Suppose an object is moving along a straight line OX with the origin at time t. Let the object be at P, where OP equal to X. It means to know the position of the object at given time t, we are required to know only one coordinate, that is distance x. Such a motion of an object in which only one coordinate is changing with time is called a one-dimensional motion. Two-dimensional motion. Suppose an object is moving in xy plane with origin at O, figure B, we can see here. At time t, let the object be at P, whose coordinate P, x comma y. It means to know the position of the object moving in xy plane at a given time t. We are required to know the two coordinates, that is distance along x-axis and y-axis. Such a motion of an object in which two coordinates are changing with time is called two-dimensional motion. Thus, motion of an object is said to be two-dimensional motion if 2 out of 3 coordinates specifying the position of an object change with respect to time. In two-dimensional motion, the object moves in a plane. For example, the earth revolving around the sun, a billiards ball moving over the billiards table, etc. Three-dimensional motion. Suppose an object moving in space having 3 mutually perpendicular axes labeled as x, y, and z axis with origin at O. Figure C. At time t, let the object be at P, whose coordinates be x, y, z. It means to know the position of the object in space at a given time, we are required to know 3 coordinate, that is distance along x, y, and z axis. Such a motion of an object in which 3 coordinates are changing with time is called three-dimensional motion. Thus, the motion of an object is said to be three-dimensional motion if all 3 coordinates specifying the position of the object change with respect to time. In three-dimensional motion, the object moves in space. For example, a flying aeroplane or bird, the random motion of gas molecules, etc. Scalars and vectors. Scalars, the physical quantities which have only magnitude but no direction, are called scalar quantities or scalars. For example, mass, length, time, distance, speed, work, etc. Vector, the physical quantities which have magnitude as well as direction, are called vector quantities or vectors. For example, displacement, velocity, acceleration, force, torque, gravitational intensity, etc. List of scalar and vectors. Scalars: mass, length, time, distance, speed, work, energy, volume, density, power, pressure, electric potential, gravitational potential, magnetic potential, resistance, electric current. Then we have vectors: weight, displacement, velocity, acceleration, force, torque, electric field, gravitational intensity, momentum, impulse, dipole moment, current, density, temperature gradient. Distance and displacement. Distance, that length of the path traversed by a body, is called the distance traveled by it. The path may not be straight. It is scalar quantity. The SI unit of distance is meter and CGS unit is centimeter. Displacement. The shortest distance from the initial to the final position of the body is called the magnitude of a displacement. It is direction from the initial position to final position. It is vector quantity. The SI unit of displacement is m and CGS unit is centimeter. Note, the displacement of an object in motion can be positive, 0 or negative. Difference between distance and displacement. Distance, it is actual path traversed by the object in a given time. Displacement, it is the shortest distance between initial and final positions of the object in a given time. It is a scalar quantity. Displacement, it is a vector quantity. Distance, it is always positive. Displacement, it is positive, 0 or negative depending on direction. Distance, it can be more than or equal to the magnitude of displacement. Displacement, its magnitude can be less than or equal to the distance, but can never be greater than the distance. It may not be 0 even if displacement is 0. Displacement, it is 0 if distance is 0. Speed and velocity. Speed. The speed of a body is the distance traveled by a body in a unit time interval. That is, it is a distance traveled by a body in 1 second. It is a scalar quantity. It is generally represented by letter mu or v. If a body travels a distance s in time t, then its speed is v equal to distance by time t, s by t. SI unit of speed is meter per second, or CGS unit is centimeter per second. Uniform speed. A body is said to be moving with uniform speed if it covers equal distance in equal intervals of time throughout its motion. If a body moves with uniform speed v, the distance traveled by it in time t is s equal to v into t, velocity into time. Non-uniform or variable speed. If a body said to move with non-uniform or variable speed if it covers unequal distance in same intervals of time. Instantaneous speed. If the speed of a body keeps on changing continuously with time, its speed at any instant is known as the instantaneous speed. The speedometer of vehicle measures the instantaneous speed. Average speed, the ratio of the total distance traveled by the body to the total time of journey, is called the average speed. Average speed equal to total distance traveled divided by total time taken. In case of a body moving with uniform speed, the instantaneous speed and the average speed are equal. If a particle travels distance s1, s2, s3, etc. with speed v1, v2, v3, etc. Respectively in same direction, the total distance traveled equal to s1 plus s2 plus s3 ... Total time taken s1 divided by v1 plus s2 divided by v2 plus s3 divided by v3. Average speed, then we have s1 plus s2 plus s3 divided by s1 divided by v1 plus s2 divided by v2. So if s1 equal to s2 equal to s, that is the body covers equal distances with different speeds, then we have v acceleration into velocity equal to 2 s divided by s 1 divided by v1 plus 1 divided by v2 equal to 2 v1 into v2 divided by 2 v1 plus v2. So this is the formula. It means average speed is equal to harmonic mean of individual speeds. If a particle travels with speed v1, v2, v3, etc. during time intervals t1, t2, t3 respectively, then the total distance equal to v1 into t1 plus v2 into t2 plus v3 into t3. So average speed equal to v1 into t1 plus v2 into t2 plus v3 into t3, like that, divided by t1 plus t2 plus t3. So if t1 equal to t2 equal to t3 equal to tn equal to t, we say as a t, then v average velocity equal to v1 plus v2 plus v3 plus vn t divided by n t equal to v1 plus v2 plus v3 up to vn divided by n. It means average speed is equal to arithmetic mean of individual speed. So we can say that average speed is equal to arithmetic mean of individual speeds. Note 1. If a particle moves for two equal intervals of time of different speeds, then v acceleration into velocity equal to v1 plus v2 divided by 2. If a particle moves distance at a speed v1 and come back with a speed v2, then v acceleration into velocity to v1 into v2 divided by v1 plus v2. Velocity, the rate of change of displacement with time, is called then velocity. And that is, it is the displacement of the body in 1 second. It is a vector quantity. It is represented by the symbol mu or u or v. For velocity, both its magnitude and direction must be known. The SI unit of velocity is meter per second and CGS unit is centimeter per second. Uniform velocity. If a body travels equal distances in equal intervals of time along a particular direction, the body is said to be moving with a uniform velocity. If a body moves with uniform velocity, the displacement s of the body in a time interval t is given as s equal to v into t. Non-uniform or variable velocity. If a body moves unequal distances in a particular direction in equal intervals of time, or it moves equal distances in equal intervals of time, but its direction of motion does not remain the same, then the velocity of the body is said to be variable or non-uniform. For example, the motion of a body in a circular path with uniform speed is with variable velocity because in circular path, the direction of motion of the body changes continuously with time. In case of motion with non-uniform velocity, we specify the instantaneous velocity and the average velocity of the body. Instantaneous velocity, for a body moving with variable velocity, the velocity of the body at any instant is called instantaneous velocity. Average velocity, if a velocity of a body moving in a particular direction changes with time, the ratio of displacement to the time taken for the whole journey is called the average velocity. Thus, we have formula average velocity equal to displacement divided by total time taken. Difference between speed and velocity. Speed, the distance traveled by a moving object in 1 second is called its speed. Velocity, the distance traveled by a moving object in 1 second in a particular direction is called its velocity. Speed is a scalar quantity, velocity is a vector quantity. The speed is always positive, the velocity can positive or negative depending on the direction of motion. Speed in one round in a circular path, the average speed is not zero. Velocity in one round in a circular path, the average path of the average velocity is zero. Acceleration and retardation. Acceleration, the rate of change of velocity with time is called the acceleration of the body. Acceleration equal to change in velocity divided by time, or a equal to v minus u by t, or v equal to u plus at. Acceleration is vector quantity. It is represented by a symbol. The direction of the acceleration is the direction in which the velocity changes. The SI unit of acceleration is meter per second and CGS unit is centimeter per second. The acceleration does not determine its direction of motion. The positive or negative sign of acceleration simply tells us whether the velocity is increasing or decreasing with time, where as positive or negative sign of velocity depends on its direction of motion. Mathematically, velocity divided by time, if a body moves with constant velocity, then velocity divided by time equal to 0. Thus, in uniform motion, acceleration does not exist. Uniform acceleration, the acceleration is said to be uniform or constant when equal changes in velocity take place in equal intervals of time. The motion of a body under gravity is an example of uniform accelerated motion. Variable acceleration, if the change in velocity is not the same in the same intervals of time, the acceleration is said to be variable. Acceleration due to gravity. When a body falls freely under gravity, the acceleration produced in the body due to Earth's gravitational attraction is called the acceleration due to gravity. It is generally denoted by the letter g. If a body falls down, its velocity increases with time, so the acceleration is plus g, while if the body moves vertically upwards, its velocity decreases with time, so the acceleration is minus g. The average value of g is 9.8 meter per second square, or near by 10 meter per second minus 2. Actually, it varies from place to place. Thus, if a body falls freely under gravity, its velocity increases at rate of 9.8 meter per second. That is starting from rest. After 1 second, the velocity will be 9.8 meter per second. After 2 seconds, the velocity will be 2 into 9.8 equal to 19.6 meter per second, and so on. Similarly, if the body is projected vertically upward, its velocity decreases at a rate of 9.8 meter per second. If a body is projected vertically upward with an initial velocity of 49 meter per second, after 1 second, its velocity will become 39.2 meter per second. After 2 seconds, its velocity will become 29.4 meter per second, and so on. It may be noted that the value of g does not depend on the mass of the body. Hence, if two bodies of different masses are simultaneously dropped from a height, both will reach the ground simultaneously if the effect of the air friction and buoyancy due to the air is neglected. Retardation. If the velocity of the body decreases with time, the motion is said to be decelerated or retarded. Thus, retardation is a negative acceleration. In general, acceleration is taken positive while retardation is taken negative. Equations of uniform accelerated motion. They are following equations for the motions of a body moving with a uniform acceleration, which give the relationship between the initial velocity and final velocity, acceleration, time of journey, and the distance traveled. V equal to u plus at, s equal to half u plus v multiplied by t, ut plus half at square, v square plus u square plus 2s, s equal to u plus half a2n minus 1, so as an distance covered by the body in nth second. Equation of motion of the free falling body. The motion of the freely falling body from a height, or the motion of the body thrown vertically upwards from the surface of the earth, is one dimensional motion under gravity. The acceleration of a vertically falling body is acceleration equal to plus g, and retardation of a body going vertically up is a equal to minus g. For a body falling down from a height h initially, rest mu equal to 0. Equation of motion are v equal to gt, h equal to minus half gt square, v square equal to 2gh. Similarly, for a body thrown vertically upwards from the earth's surface with initial velocity u, the equation of motion are v equal to u minus gt, h equal to ut plus half gt square, and v square equal to u square plus u square minus 2gh. At the highest point, v equal to 0, therefore t equal to u divided by g, and h maximum equal to u square divided by 2g. Graphical representation of linear motion. The linear motion of the body can be studied with the help of the following graph: displacement time graph, velocity time graph, and acceleration time graph. Displacement time graph. In the displacement time graph, the time is taken on x-axis and the displacement of the body is taken on y-axis. From this graph, we can determine the velocity of the body from the displacement time graph of an object. We can know the nature of motion of the object. Let us consider the following situations. Case 1. If the graph is a straight line parallel to the time axis, the object is stationary. Case 2. If the graph is a straight line inclined to the time axis, the motion is with uniform velocity. The velocity of a body can be obtained by finding the slope of the straight line. In this case, the displacement is directly proportional to the time. Case 3. If the graph is curved, the object moves with a variable velocity. The velocity at any distant instant can be obtained by finding the slope or gradient of the tangent drawn and the curve at the instant. Note, in displacement time graph, if the slope is positive, the body is said to be moving away from the starting point or a reference, but if the slope is negative, the body is said to be returning towards the starting or reference point. Velocity time graph. In the velocity time graph, time is taken on x-axis and the velocity is taken on the y-axis. Since velocity is a vector quantity, the positive velocity means that the body is moving in the certain direction away from its initial position, and the negative velocity means that the body is moving in the opposite direction, that is towards the initial position. From the velocity time graph, we can determine the displacement of the body in a certain time interval. Since velocity into time equal to displacement, the area enclosed between the velocity time sketch and x-axis, that is the time axis, gives the displacement of the body. The acceleration of the body. Since acceleration is equal to the ratio of change in velocity and the time taken, therefore the slope of the velocity time sketch gives the acceleration. If the slope is positive, it is accelerated motion, and if the slope is negative, the motion is accelerated and retarded. Now we can consider the following cases. Case 1. If the body is in motion with uniform velocity, the velocity time graph is straight line parallel to the line axis as shown in figure. Case 2. If the body is in motion with uniform acceleration, the velocity time graph is straight line inclined into the time axis. The slope of the line gives the acceleration. If the motion is with uniform retardation, the velocity time will be straight line inclined to the time axis with a negative slope. The velocity time graph can never be straight line parallel to the velocity axis, because it would mean that the velocity is increasing without any increase in time, that is, acceleration is infinite, which is impossible. If the body initially is not at last, but it is moving with some uniform velocity, and then it accelerates, the velocity time sketch which not start from origin, but it will start from the point on the velocity axis corresponding to the initial velocity of the body. Case 3. If the body is in motion with variable acceleration, the velocity time graph is curve, as you can see in case 3. Acceleration time graph. In the acceleration time graph, time is taken on the x-axis and the acceleration is taken on the y-axis. From this graph, we can find the change in speed in certain interval of time. The area enclosed between the acceleration time sketch and the time axis given the change in speed of the body. Let us consider the following cases. Case 1. If the body is stationary, or if it is moving with uniform velocity, the acceleration is 0. The acceleration time graph in such a case is a straight line coinciding with the time axis. Case 2, if the velocity of the body in motion increases uniformly with the time, the acceleration is constant. In such a case, the acceleration time graph is straight line parallel to the time axis on the positive acceleration axis. Case 3, if the velocity of the body decreases at a constant rate, the retardation is constant. The acceleration time graph is a straight line parallel to the time axis on the negative acceleration axis. Case 4, if the velocity of the body changes in an irregular manner, the acceleration is variable. The acceleration time graph will then be a curve of any shape. Relative velocity. When we consider the motion of a particle, we assume as a fixed point relative relation to which the given particle is in motion. Va and Vb are velocities of two bodies related to Earth. The velocity of B relative to A will be given by Vb minus Va, final minus initial. If two bodies are moving along the same line in the same direction with velocity V and Vb related to the Earth, the velocity of B relative to A will be given by, if the bodies are moving towards or away from each other as direction V and Vb are opposite, the velocity of B relative to A will have magnitude. So V Ba equal to V minus Va equal to V plus Va. Thus the motion of two bodies relative to each other is the difference of velocities of the two bodies if they are moving in same direction, and is the sum of two velocities if they are moving in opposite direction. Projectile motion. If an object is given an initial velocity in any direction and then allowed to travel freely under gravity, the motion is called projectile motion. In case of projectile motion, it is assumed that acceleration due to gravity is constant and the effect of air resistance is negligible. Projectile motion is a two-dimensional motion and can be regarded as simultaneous superposition of two motions, one horizontal with velocity mu cos theta and acceleration equal to 0, and the other vertical with velocity mu u sin theta and acceleration minus g. Following terms are used. Projectile motion trajectory. It is the path followed by projectile. Equation of trajectory is y equal to tan theta x minus g divided by 2 u square cos square theta into x square. This is an equation of the type of y equal to ax minus bx square, which represents a parabola. So the path of the projectile is a parabola. Time of flight. The total time taken by the projectile to go up and come down to the same level from where it was projected is called the time of flight. The equation of time of flight is t equal to 2t 2 u sin theta divided by g. Horizontal range. It is a horizontal distance traveled by a body during the time of flight. The equation of horizontal range r equal to u square sin 2 theta divided by g equal to u square 2 sin theta cos theta divided by g. For maximum range, theta equal to 45 degree. Maximum equal to u square divided by g is a equation. That is, projectile will have maximum range when it is projected at angle of 45 degree to the horizontal. Maximum height h equal to u square sin square theta divided by 2g. At the highest point, the projectile possesses velocity only along horizontal direction. At the highest point of projectile path, the velocity and acceleration are perpendicular to each other. In projectile motion, the particle returns to the ground at the same angle and with the same speed with which it was projected. In projectile motion, kinetic energy is maximum at the point of projection or point of reaching the ground and is minimum at the highest point. There are two times for which the projectile travels the same vertical distance, and sum of these timing is equal to the total time of flight of projectile. The time of flight, the horizontal range, and the maximum height are independent or of mass of projectile. Note 1. When the range is maximum, the height h reached by the projectile h equal to u square sin square 45 degree divided by 2g equal to u square divided by 4g equal to r maximum divided by 4. The maximum height attained by projectile is equal to 1/4 of its maximum range. For height h to be maximum, equal to u square sin square 90 degree divided by 2g equal to u square divided by 2g. That is, a projectile will have height h capital maximum when it is projected vertically, that is theta equal to 90 degree. Relation between h maximum and r maximum. H maximum equal to r maximum divided by 2. A projectile has the same range at angle of projection theta and 90 degree minus theta, or 45 degree plus theta, and 45 degree minus theta. Circular motion, motion of an object along a circular path is called a circular motion. Uniform circular motion, when an object follows a circular path at a constant speed, the motion of the object is called uniform circular motion. The word uniform refers to the speed which is constant throughout the motion. In circular motion, since the velocity of the object is changing continuously in direction, its direction of motion at any instant is along the tangent to the circle at that instant. The object undergoes acceleration. Therefore, circular motion is called accelerated motion. That is, circular motion is an accelerated motion. Motion of moon around the earth, motion of satellite around its planet are called example of circular motion. Difference between uniform linear and circular motion. Uniform linear motion, the direction of motion does not changes. The direction of motion changes continuously. The motion is non-accelerated, the motion is accelerated. Angular velocity, the angle subtended by the line joining the object from the origin of the circle in unit time interval t is called angular velocity. It is generally denoted by w, and w equal to theta divided by t. Angular velocity is a vector quantity. Its direction is same as theta, direction of theta. Relation between linear velocity and angular velocity. If t equal to time period and time taken by the object to complete one revolution, n equal to frequency number of revolution in 1 second, then t equal to 1 divided by n, or n equal to 1 divided by t, or n t equal to 1. When an object completes one revolution, the angle traced at its axis of circular motion is 2 pi radian. Hence, w equal to 2 pi divided by capital T, 2 pi n, and w equal to theta divided by t, and n equal to 1 by t. In revolution, the object traverses 2 pi r distance circumference of circular path. Linear velocity equal to 2 pi r t equal to wr, or v equal to wr 2 pi divided by t equal to w. Linear velocity equal to angular velocity into radius. Angular acceleration. Angular acceleration of an object in circular motion is defined as the rate of change of its angular velocity. It is denoted by alpha mathematically. Alpha t or mu w divided by t, or w divided by t, like this way. SI unit of angular acceleration is radian per second square, and its dimension formula is m0 l0 t minus 2. Relation between linear acceleration and angular acceleration. We know that linear velocity v is related with the angular velocity w by the relation v equal to wr. Differentiating it with respect to time, we have change of velocity divided by change of time equal to change of angular velocity divided by change of time into r equal to acceleration equal to alpha r, where a is linear acceleration and alpha is angular acceleration. Then we have Newton's laws of motion, which we'll study afterwards. Thank you, all of you, to be here. Okay.